So, welcome back to network security. So, we have been at the topic of secure data in use. So, how can we protect our data from various computing parties? So, this is where we are currently at. And the overview was we started first with the simple server where you just trust that everything works fine and they keep their regulatory and legal promises to secure your data, to handle it properly. But the issue and the risk is always that you still have to trust, and there's no guarantee, and this guarantee has often not been achieved. So we have the issue that these servers lose data. Then the second point, we looked into differential privacy, where the idea is that to any given number that is stored there, you add some kind of distribution, some kind of number in addition to it that changes the value. So if this is the number, you add some random value or you subtract some random value, and it's depending on how many it depends on how the differences are. So the more numbers you have, let's say there are many entries with around 1000, then you don't have to add too much variance, too much noise to it, too much randomness, because there are anyway so many that your individual number is not detectable in it. So if you have 1000 numbers there in it, then it doesn't make a difference whether you are the number 1001. So then it's sufficient to add less noise. But if there are very few numbers only, let's say 10, then you have to give large numbers to it, much more noise, so that your individual number is more concealed. And then the main question is where do you apply this differential privacy? So one option is that you have this kind of trusted server, trusted curator, where everybody provide their data in clear, and the data that is submitted to this curator is valid, so it's the true one. And only if there are queries from outside, untrusted querier, they get the noise in the answer. So basically, you compute the answer with some noise, so that in general it seems correct, and it might be very close to the true result. But it's actually not, so it's the noise added there. The issue here is that a trusted curator has all knowledge. That's again the issue. So the alternative would be to add noise to each individual data that is provided to the curator, to the aggregator. So if you, for example, report your age, and your age is between 0 and 100, then you add plus minus, 50, and then the results will not be really linked to you. The problem is then everybody needs to provide the same pattern. So everybody needs to know, okay, to our age we have to add a specific plus or minus 50. So in this bracket, to pick some random number, it can also be minus 3, it can be plus 47. And with sufficient many data providers, these noise will even out. So in average the noise is 0, and the more data entries we have, the more reliable the statistics can be. So if we compute here the average, then it will be quite true. If we compute here the sum, that will also be fine. A min and max will be more problematic, but at least one kind of statistical aggregation, such as average and sum, we can compute. Okay, so this is differential privacy. By this we do not conceal. We do not reveal our real numbers, but in rough estimation, the numbers are still fine. Then we looked into the computation and trust in hardware, and especially in the solutions, let's say by Intel Security Guard extension. There are also similar approaches by AMD and other CPU manufacturers, where the main idea is that you have some kind of trusted, protected zone in your CPU, which is only accessible to signed off and to verified algorithms that Intel verified himself. So even the administrators and root users cannot access this zone. So there you can process keys, there you can open them, there you can reveal them, because no external process can enter it. Even with super user permissions, it cannot be entered. And the root of trust, and how does this work, is the companies that want to use this kind of platform, that want to provide and use this secure algorithm area, and they have to request from a service provider, from Intel or so, that they have to show their algorithm that it's not interfering with any kind of secrets. Then they get some kind of attestation, and this attestation they can show to the client, look, this is my algorithm that's running on the code and has been verified. I'm not cheating in this algorithm, and you can trust me to run this specific algorithm that has been verified by Intel on your code. And so the code can be executed, data can be handed over to that part, and then no secrets are revealed. At least this is the claim. So it's very efficient because it's running in quite plain text on the CPU. There are also some optimized databases based on this, but the problem is, well, it's if a malicious attacker, even with a verified algorithm by Intel, has control over his machine, there are several ways how he can still try to obtain knowledge from this enclave, especially by accessing somehow the memory or the cache. So, for example, if you can try to use some CPU internal characteristics, how memory is processed, in order to learn what kind of bits are in the enclave, maybe to learn the key from that. Yes. So, and another drawback is in its usability. Each algorithm needs to be verified. So Intel has to look over each algorithm and to agree, and this is limiting the companies to use it, because that's really slow. Okay, then we looked into homomorphic encryption, and here the idea is that the data is encrypted. This is the realm of the compute center. The compute center receives the encrypted data. It can operate various algorithms, functions on the encrypted data. At the end, it has some encrypted result, and then it can send it out to the user, and the user is in this realm, can then decrypt the data and see that the results are correct. And the reason is that there's some interaction, there's some link between the operations on the plaintext level and the operations on the encrypted level. So, for example, in RSI that we looked into, you can simply multiply and divide. This is still valid in the encrypted space. In other encryption schemes, maybe an XOR on the plaintext results in the multiplication on the ciphertext, or plus and minus results in multiplications and divisions on the encryption space. So, depending on the encryption scheme, you have to see what's the corresponding operation on the encrypted scheme, but then it also works. What is the drawback? The drawback is that here in the encryption you use a key, and here in the decryption you use also a key. That's fine, that's okay, if you have one single key. Having one single key means you have one single person providing the data. What's not possible is that several people contribute this, to that encryption scheme, contribute to that computation, because that would require that they use the same encryption key, they use the same decryption key. And of course you can do it, you can share a key with millions of people, but then it's not anymore secure. So especially the people can read the data of other people. Okay, another issue that was happening here is that if you just simply use the plaintext computation and you operate on integers, you always get the same ciphers. So, I mean, assuming that you have the same key, yeah, the same key is used, and if you have such a computation as we have seen, then you can derive from this that this is 0, and then somehow if there's a multiplication, then you can derive what is a 1, and then if you have if you know what 0 and 1s are, and you see somewhere, I don't know, x plus 1 equals y, then you know the relationship between x and y, and then if one of them, I mean, over time you can learn more and more about links between the different numbers in the encryption space, in the cipher space, and you could step by step basically resolve what the numbers behind these are. So homomorphic encryption introduced some kind of noise so that you get some, not the exact encryption, but let's say 0 is encoded to 0.00001, and then it's a little bit different, and then the encryption is different. But the problem is if you add in any operation some kind of noise, after 10,000 operations or 100,000 operations, you would, let's say every time there's a noise of this value, then after 100,000 operations you already increase your number by 1. So then you have the wrong numbers. So noise accumulates, that's the issue, can be only used for a limited number of operations. And the idea was here to introduce fully homomorphic encryption 15 years ago. And basically you have, let's say, I don't know, 10,000 operations available before the noise is too large. So what you do is that you first reset the noise and then perform your operation. And there's still a little room. So basically the relationship is you have one computation, and you have the re-encryption cost is very high, and the operation cost in contrast to this is very low. So you have, let's say, an overhead of 10,000 operations in contrast to one single usable operation. So it's much slower than operations on regular numbers. Still, this is basically one very promising approach, and it has been used in various databases such as CryptDB or so, where basically the idea was to use regular databases to regular applications, regular users and so on. And what happens is the application interacts with a proxy, database proxy, so it mimics that it's a real database. It can store data, it can deliver data, but what it actually does is if it should store data, it encrypts the data and stores it in the modified database, in the unmodified database. And if there's some kind of computation requested on the data by the application, the corresponding database proxy knows how to translate it depending on the encryption scheme, and can perform this kind of computations and use the unmodified database for its usage. So basically you added some additional elements in the interfaces which then implement the security. Okay, and then we were roughly here. Yeah, so basically also it has been discussed that depending on which operation you run, so addition and multiplication, that's quite nice, that's fine. So multiply is fine and sum is fine, and these are more in the stronger schemes, stronger operations. But comparisons already getting more revealing. A join is even more revealing, so especially join is revealing equality between various numbers. So even if they have noise, so let's say you have two databases which should be joined by the age of the people or by the user ID of the people. I don't know. You'd have just two databases joined by user ID. Then, once the join operation is successful, obviously you learn user ID X in one column with a specific noise and user ID X with another noise in another column, that they are equal, although the noise is showing that they are different. So you learn more about the data. So you have basically some kind of a spread of which operations are not revealing anything and which operations are revealing data. such as search, join, and min-max order. And so if you order the numbers by size, obviously, then you reveal the whole order of the values. So you can see what's the lowest number, what's the highest number, what's second highest, and so on. So and then also you lose data. So it's somehow limited. Comes also with some overhead, that's fine, but it's commercially in use. And another limitation is also here that only one single key can be used. So it's more for the use case that the application wants to be protected. So if you have this setup, you have one application with one specific key and the database that it's operating on. So basically there you have one application as a user with its key, but you cannot join data from various sources. Okay, coming to some further extension in homomorphic encryption domain, and these are encryption schemes for time series databases, such as, so typically use case often you have time series, I don't know, a car is driving around collecting GPS information, where it is, what's its current load of state, so how much it's charged and so on. And you want to store that periodically by time where the car drove along. Or if you have IoT devices, they capture some humidity and sensor data and so on, then it's also time-based and you want to store it in some kind of database. And there are also some kind of time series optimized databases for this, which basically use some more clever key generation. So what are time series data? It's basically that you have these regular entries. And the idea is for this clever key generation that the key is just simply adding some value to it. Yeah. -1, +5, and so on. And if you aggregate over it, and then you basically can also aggregate the keys. That's the idea. So that the encryption scheme itself is not too complex, you just add a number. And you can aggregate the keys, so if you know, okay, if I sum up all of these keys and the sum is, I don't know, -17, then I can take the aggregate of this domain. So typically, what do you want to show? Let's say this is the time, and you want to show how the sensor data was going along. Yeah. Then you either have data, so individual values, or if you want to summarize, I want to have it in hourly plots. So what was the average sensor value for a specific an hour? Then you can also aggregate the sum or the average of all values within the hour bracket. That's 3,600 seconds. You compute this average. You also apply the encryption on it, and then you can store on the fly basically all these aggregations. So you implement on the fly aggregation for minutes, for hours, for days, so that you can simply, when you want to visualize your sensor data, basically you have the corresponding keys, the corresponding values prepared, and you don't need to encrypt and re-encrypt and so on based on individual values. Okay. Limitations, so basically then you have for all of these time frames, so let's say this is a second, every time you have the encryption, but you have also the encryption for the minute, and if it goes higher, then you have from T0 to Tn for the minute, for the hour, and so on. So you have already this pre-advanced computations, but it's also very limited to that. So no other SQL commands. It's just as aggregation over time, and that's it. But for one single purpose, such as storing, let's say, sensor data securely and visualizing just the results, or delivering the results to the legitimate query starter, then you can store the data in this encrypted format quite conveniently, but it doesn't support something more. So basically you have often the issue, either it's efficient like this scheme, but it's then limited in what you can use it for, or it's general purpose, such as the homomorphic encryption, and then you are quite slow. And even the homomorphic encryption is limited in its sense that it can only support one key. So there are even more advanced schemes that allow you to also to combine data from various users, but that are, on the other hand, even slower than this factor of 10,000. So let's have a look at that, how we can make it slower, but at the same time more secure. And here we look into the use case, basically coming to this trusting, having distributed trust that not all parties cheat. And let's see what kind of options we have there. So the idea is to have a distributed system where the computing parties only have partial, distorted, encrypted data that is individually useless. And let's have a look how we can compute on this. We had a look at fully homomorphic encryption, and so this is already basically done. Very efficient, can be very efficient, simple to use, as we've seen with time series databases, but it's limited to few operations. Now we will have a look at two other options, secret sharing and garbled secrets, to complete this lecture. And let's start with the garbled secrets approach. This is Turing complete, so you can compute anything that you want, any kind of inputs, full range of algorithms, but it's so slow that it's only sufficiently efficient for small programs. So you can compute everything, but not in your lifetime. And the idea here is not just the data is hidden, but also the algorithms are hidden. So you provide the input, you provide the algorithm, in an encrypted form, and you get the results also in an encrypted form. So basically you deliver everything to the compute party, hand everything over, and then it takes some time to compute, and then you get the results. So, and the computing party, for homomorphic encryption, so it knew the operations that it executed. Here it doesn't know anything. It doesn't even know what it's computing. That we will look at. And we will also look at some kind of approach where, so this is one machine, and these are potentially n providers, but data providers, can also be one. And here you have n data providers. This is optimized for that purpose, so that you really have potentially many data providers. So we'll have to see how the data is encrypted then. And the computing party, where you need at least 3+ computing parties, are not able to read it. Okay, let's start with this garbled circuits. This is now the two-party computation example, and what it is based on is on a scheme. It's called Yao's oblivious transfer, and the main idea is that you have some kind of storage where you say which message you want. So Bob has here message 0 and message 1, and you say, you make your decision, your selection. Bob delivers your selection, but you did not reveal was it 0 or was it 1. So you can basically retrieve data without revealing which data you retrieved. This is the core element that we first need. So a moment. Okay. And what is this B? How can you not reveal what you have? You send over a key and a corrupt key, but you do not reveal. Basically, you send over two keys, and it is the receiver Bob can check Basically, you send key A, no? Key A and key B. So you send over 2 keys. Bob can verify that together they fulfill the property that one is valid and one is bogus, but it doesn't know which one. Yeah, so it's like having, I don't know, if let's say, I'm just thinking whether we have some example for this. No, I don't know. So it's basically some mathematical function like if you multiply the 2 keys, then a specific value comes out, but one of them, and then with this constraining property, both cannot be keys because they have to, when multiplied, result in a specific value, but you don't know which of the 2 factors is actually the key and which one is has been computed in a way that it fulfills this criteria. So, but still it's provable, both are keys, and one of them is not a valid key. But you don't know as Bob which key which of them is valid. And basically then what you do is you encrypt M0 with key A and key B you use to encrypt M1. And then you send both results over, and you know one of the keys are not valid. So one of the results will not be retrieved, but the other one will be correct. But you did not learn which of the 2 results is the correct one. So this is basically how this oblivious transfer works. It's how the 2 keys are selected so that they have the property, one is valid and one is not. And for delivering the data, M0 and 1, both keys are used. And then, as Bob, you also know, one of the values is not delivered because it's actually a false key. It cannot be decrypted also. Okay. Yeah. That's basically also here. So basically the corrupt key is based on a way that its property is that both together fulfill a specific mathematical property. Okay, so now so this is the building block. And now we are building the garbled circuits, and they should support various complex algorithms. How is this done? So first you take an algorithm. Yeah. Then you create a directed graph of arithmetic operations. So if you have, I don't know, A plus B times C, this is, then you create this kind of directed graph of algorithmic operations, such as a tree structure. There's also AND. So basically you derive this kind of, so first you derive this kind of property, I mean how the tree structure is, and then you select one specific, basically you do it for every individual one, but you create the Boolean circuit. So basically any kind of operation that you have can be derived to basic Boolean gates, such as XOR, AND, NOR, and XOR, and so on. So let's take this example. So here we are at the state. So we have this algorithm. Let's draw it somewhere else. So we have this algorithm. A plus B times C. This will be resulting in a plus A multiplication BC. Then for any of these building blocks where you have one operation, you derive the Boolean expression. So the Boolean circuits, how the gates would be to be set. So let's say that now, let's make it different, because here we have A and B. Let's make it this way. Put here C, we put here C, and here we put AND. So AND. A, B. So now we want to compute A and B, and there we describe the gates. So A and B is if both are 0, 0. A and B is 0 if A is 1 and B is 0. If B is 1 and A is 0, it's also 1. Only if A and B are 1, then A and B is 1. Okay, so and now the trick comes. You encrypt the circuit by replacing the bits with keys. That means from 0 we identify it as if the key corresponding to 0 comes and the key corresponding to 1 comes, then this key should be the output. If the key from A x1A comes and the key from B x1B comes, then this should be the output, this key. These are all symmetric keys. And how do we implement this function? It's basically we encrypt with the given keys the result. So that means if you have been given from A side this symmetric key xa0 and you have been given from B side xb0, as it has been encrypted with these keys, the result key is in the encrypted data. So basically, if the computing party on the other side receives two input values, which are these keys, x1a and x1b, then it just tries to decrypt any of these four options, and it sees, okay, this is the result I get, this is the decrypted value, and this is how you get the next key. So basically, it's a function at the computing side where you need key 1 and key 2 as an input. This is coming from A, this is coming from B, and you get key 3 as a result, and this is number C. Or as you see it here, it's basically the AND gate with the inputs of symmetric keys that has an output also symmetric key. Okay, let's see what we do with this idea. So how is it used? It is used in a way, so first, again, we have to keep in mind that if Alice wants to use this data, this kind of computation, she does not want to reveal what she is computing. Maybe to talk about this point, what is revealed here? So let's assume you are the computing party here. And you get a key, you get another key, and you can decrypt the key. Which function have you computed? You don't know. Actually, you don't know because you don't know, I mean, you just get one key that, so neither key 1, nor key 2, nor key 3 are anyhow meaningful. These are just numbers that don't have to do anything with the value 0 or 1. It's keys. I mean, you don't know whether key 1 is a 0 or a 1. You don't know whether key 2 is a 0 or 1. You don't know whether key 3 is a 0 or 1. So you cannot see the table, basically, because you could not decrypt the other values. You just had the keys for one matching pair. So you could only decrypt one value. You do not learn about the other 3 values. And you got a new key, and you don't know what it means. Because who was setting the keys? Alice, who was setting the algorithm, and who was providing the data, was setting the keys. So Alice first needs to compute this kind of encrypted circuits in order, and basically to prepare the algorithm, so that later, when she hands over the keys as an input, basically her input zeros and ones, the right result will come out. But Bob, having the algorithm, doesn't know what he's computing. And let's say that the last part of it is the garbled circuit. So if you have this kind of order, so basically you have, this is entry number 4, what we computed here. You have entry number 3, entry number 2, entry number 1. You just mix the order. You mix the order here, 1 and 2, you mix the order here, 1 and 2. It's just random in which order they will be represented, so that even from the position of the keys and the functions they compute, you do not learn anything. So you don't know in advance all zeros will be first handled. It's just different order. And these are the garbled circuits with the permuted rows. Basically what Alice was doing is to prepare the whole algorithm, send it to Bob. This is basically how she first delivered M0 and M1. And later, when she interacts with Bob, she can tell Bob, I want this key. So B, I want entry number B, without even revealing which of the two she selected. So this is how it comes together. So Alice can interact with Bob without telling him what she received, what she retrieved, what she queried for. And Bob only is in charge to resolve basically this kind of garbled circuit, get the input keys, check what next keys he can decrypt, and then follow up. So basically, we will have an example for this. But basically, so Alice hands over the input 1, input 2. Bob calculates the key number 3. Alice delivers input 3, and then Bob delivers basically the result 5, I don't know, without knowing. It's just keys that Bob sees, and Bob doesn't know what it computes. So what is the approach? How can it be used? So first, prepare and share the circuits. So Alice needs to compute any function securely. So she needs to pre-deploy, so to set up the keys, to compute these gates, these binary gates. She needs to replace the binary numbers by keys. She needs to garble the order of the keys and so on. And she sends this to Bob. So first Boolean circuit, encode all possible outcomes for all gates for any kind of input, and transfer the circuit to the computing party. Ideally, this is just, okay, let's say then this is delivered to Bob. And now Bob has the algorithm with lots of keys. And now Alice uses it, so she inputs her bits as input keys. So she tells, okay, the algorithm starts with these keys, and here are the keys for it. And then Bob can, at first, as we have seen, Bob gets the keys, key 1, key 2, derives key 4. Maybe there's another input, I don't know, let's say key 1 and key 3 are used in a function to derive key 5, and then key 5 and key 4 are used to derive key 6. Obviously, I mean, you see it, you just need the entry keys in order to decrypt the encrypted keys for the next step. Input keys allow the decryption of next key in the circuit, but without knowing what this key stands for, 0 or 1. Then you progress through the circuit until output bits are calculated, that's the result. And this is then delivered to Alice, and then only the recipient knows what meaning she associated to that result keys. Is it a 0 or is it a 1? So let's have a look. How does this look like? So Alice prepares the garbled version of the algorithm and delivers it to Bob. Delivers it to Bob, and then later on, so this is first deploy the algorithm, second use it with your input. Next, once you deploy the algorithm, she can send her encrypted form of X on her input. Bob allows Bob to obtain encrypted form of Y, so this is and then basically Bob can follow on, and through the whole computation, the computing party, Bob can never see Alice's input in an unencrypted form. Bob only gets keys, key 1, key 2, results in key 3. Bob can obtain the encryption of Y, Bob, key 1 and key 2 in the can decrypt key 3, so Bob can obtain key 3 without learning what this means. No party learns intermediate values and remains secure if the parties try to cheat. So again, here the example, if Alice provides this data, I mean, this can also be scaled to various users. So if Alice and Bob agree on some scheme, they can both provide their data that then is decrypted, so their keys are used to decrypt the resulting keys that are, I mean, you have all to prepare all these various keys. If you provide the right ones, you get the next key, and then you get the next key, and basically all other boxes that would have been available remain closed. So you cannot, if you don't get the keys for the computation, you cannot decrypt what was inside. Let's have another example. Okay, so once again, so let's say so first of all, Alice picks two random keys for each wire. So one key corresponds to 0, one to 1. Then we have 6 keys in total, because we have as an input, again, think of this, you have here 0, 1, 0, 1, and as a potential output also 0 or 1. So these are the 6 keys that you need. So this is 1, 2, 3, 4, 5, 6. Okay. If it's more complex, obviously, then you need to add more keys, and you need every key to decrypt, to have available to decrypt the next key. Yeah. So as a next step, you have these encryption schemes that basically describe what keys you need in order to get which other keys, but they are organized in a way that this is 0, 0, basically first key and 0, next key, no, sorry, first key, second key, first key, second key, first key, second key, first key, second key. And this is too obvious, so therefore it's mixed. In this case, it's like this. So this is the garbling. So that the recipient doesn't know, I mean, obviously this is just too revealing, and this is not, because it's randomly sorted. And the next time when Bob is really using something, when Alice is using it, when she sends her input bits, this is her input, and this is delivered to Bob. Bob can then check how Bob can basically unpack it, and basically that's the input of Bob, of Alice. Now comes the second key. Yeah, Alice input is the 2 keys corresponding to Bob's wire. I mean, let's talk about it in a second. So basically, when Alice delivers the second key, then Bob can continue to further decrypt the data in order to derive the next key, this one. And now the question is, where's the second key coming from? This can be also the input of somebody else. So if Alice is only providing one key and Bob is providing the other key, Alice also doesn't know. So what I want to say is, I want to talk about the case that the input is coming from Alice and coming from Bob. So in this case, we are here, Alice provided her key, and this is, this is what is now visible to Bob. And Bob has the same case, independent of whether the input of Alice was 1 or 0. So it's basically Alice could use the keys of Bob to create the corresponding answer, and now when Bob enters his values, his part, then he can decrypt the rest. So he can provide his inputs. He learns what the output is. I mean, but he does not learn whether Alice had 0 or 1 as input. So Bob doesn't learn what the input of Alice was. Yeah, Bob doesn't learn what the input of Alice was, and Alice doesn't learn what the input of Bob was. Because basically it just allows to decrypt one single result, which is then shared to everyone, and both to Alice and Bob in this case, let's say, if Bob and Alice provided the input, and both did not learn what the other party had as an input, but they learned the result. So it is depending on how you want to do it. You can also introduce further computing parties that provide input. Here's another visualization of how Bob evaluates the garbled circuit. It's like this. As I said, the first step is you have your algorithm. You create this kind of algorithmic tree that looks like this. So then you know in which order you have to process them. Then you get the input from the data provider. Then you can compute this, and you basically have maybe this key. You get further input. You get maybe that key. This is then the input here for, that's maybe this, resulting here in something. So basically go through the list of garbled circuits until you reach the end, and you have the final result that you can send somewhere to Alice maybe. I mean, it has to be to Alice, to the person who delivered the algorithm and who can interpret whether this key is a 0 or this is a 1. Okay, so Bob tells Alice the key for the final output wire, and she tells him if it corresponds to 0 or 1. Yeah. Okay, so this is Turing complete because every kind of algorithm can be mapped to gates, and every gate can be encrypted, and every gate can then be garbled. So I mean, garbling is anyway just very simple, reordering the columns and so on. So let's have an example. Let's say we have some kind of how large is the code in. So let's say if you have a simple algorithm, so the IIS algorithm or the encryption algorithms, just as a reference, IIS has 5,440 AND/OR gates, 20,000 XOR or NXOR gates, total gates 25,000. Some rather older hash functions have 61 gates, 61,000. Some more modern 132,000 gates. And if you try to compute that, this is how many bits you need. So it's 500,000 times 80 bits. So it's getting huge, and also the computation time is so far away because there's so many gates, and every gate computation that is typically done very fast on the hardware of your CPU involves an encryption, decryption, and is very time consuming. So you have very huge algorithms, and it's very, very slow. But it's Turing complete. So that might be, at one time, the future. Okay. So let's have a look at another option. Or any questions to this?
So how does Bob determine the key that he needs to provide? Because Alice determines like which keys are mapped to which value. But how does Bob know what, how to encrypt it, and how does Alice not? Well, she doesn't get that anyway. But how does Bob know what to do with his
Yeah.
value?
I think the point is that's right. So it needs to be set up in a way that that it is already pre-planned in the algorithm. So basically, if Alice wants to allow Bob to provide his input, the computation is taking place at Bob's side. So where are we? Yes. And basically, if it has, I don't know, there are 6 fields where input is required from Bob. There, Alice can tell, okay, your keys for these fields are this and that. I hand it over to you. You don't tell me the intermediate. And you do the computation by putting in your keys. And then the garbled circuit will derive what, then everything is prepared for those keys to take place.
Okay, yeah. So she provides it. But how can Bob not learn the value that Alice provided when she provides the key for it? Because he knows how to compute it.
Yeah, but he doesn't know. So if you see this one as Bob, you don't know. The keys, both what Alice gets, I don't know, this might be a key, and this might be a key, and the resulting key is, I don't know. You don't know whether in Alice world, what of them is 0, what is 1. So you can only use the input of Alice to identify, basically you check where you can encrypt it, and then you get a new key, but you don't know what Alice associates with this key. You also don't know what kind of operation was computed. You might know that you provided a 1, but you don't know, it's basically a star coming from Alice, a star operation from Bob, from the operation. This is the operation from Bob, and this is again something that you don't know as a result because it's a key that Alice pre-planned.
Because else I could just
yeah.
If I
Otherwise you could.
I could just write a 0 and then I don't know if it's like a 0 or then I can see how it changes and determine which values, but because I don't know the operation.
But that's also a good point what you said, if I see how it changes, because it's also recommended to use it only once. So you make this whole setup, you compute all the keys, and if Bob would be able to try out new inputs every time and see what's the output and whether the same output comes with different inputs from him, then Bob could learn over time how his input reflects to the output, at least where some equal output comes along. So let's say if he always encrypts, provides a 0, and then the result is always the same, independent of Alice's input, then probably it's a multiplication or so. And Bob could learn what operation he's running, could derive what Alice is doing, what Alice's input could mean. So actually, every algorithm should only be run once, and for the next time, new keys should be deployed so that there's no learning possible. It's very expensive. And it's also mostly limited. It's very expensive, and still you cannot scale it to millions of users providing data. That would be just too many keys. So therefore, next use case. Let's learn, for example, at first something about secret sharing. How many people can share a single secret without one individual having the key himself? So there's a secret sharing scheme, SAMI secret sharing. And the idea is that there's some kind of polynomial create function, like here, so with this wave. And then at specific points, x1, xi, you have this y points, so the function values. So this is a point, this is a point, this is a point, this is a point. And as you know, if you have a polynomial of the factor t, it's sufficient to have t many points to recreate the polynomial. So basically, if you have, I don't know, yeah? So if you have the largest number is x to the power of t, then you need t points to get the full function recovered. And the secret is where it cuts, let's say, what's at x equals 0. So what you can do, and this is the nice thing now, so you need at least t many members to recreate it, but you can have more. I mean, you can have more points, I don't know, t plus 5 or so, and it's then sufficient that t out of n participants agree to bring together their numbers, their points, and then they can reconstruct the polynomial fx and derive the secret s. And this is how, let's say, t out of n can have a shared secret. Okay, so the next step, what kind of nice properties do we have? So let's say we have a secret which is here, and we have a secret that is there, and if we add the function, so this is the function f, this is the function g, this is the function f plus g, then also the secrets are added. So as you see, if we add the two functions, then also the t plus s is added. So where it is basically, if x equals 0, where it cuts the y-axis. So what you could actually do, and this will become the basis of a new encryption scheme, is that yes, we will see. Okay, so at least you can do very simple operations like plus and multiplication. So multiplication with a factor, multiplication with two values, two secrets is more complex. Limited operations. So let's say, but based on this, we can build a new encryption scheme. And this is what I want to present you. And the idea is that you don't need to have too many complex encryption schemes if you just distribute the values. So let's say somebody having only this point cannot reconstruct the key, the secret T, or having only this point doesn't tell anything about this. And as long as not T many parties interact to cheat, to let's say open their values and what points they have, you can do any kind of computation. And this is the basis for the following idea. So let's compute very securely our age, for example. So we are 6 people, and now we want to privacy preservingly compute our age, something that we have in common. So what I could, for example, do, I take a very large number and add it to my age, I don't know. So I send the result hidden in secret to you, and then you add your number. So this is what I sent you, and now you add your number without telling anybody. Yeah, it's internally in you. I don't know. What age? How old are you? 28. So it's okay. And sorry. So okay, let's make it this way. Let's make it more clear. So we have here 6 people, and the first starts with a very large number and sends to the next party 640. So it's unclear what age he is, and unclear what big number was added. And then you add your number, 28. We just reveal it for the example, but otherwise it's hidden. And this is the information that you share to the next What's your age?
24.
24. So this is the information what you share. You add your number. And as you see, the numbers are quite meaningless. They don't reveal anything what's related to you. What's your number? 17.
23.
Okay. So, try it, yes.
25.
Okay. So this would be the number that you hand over. So, and you're 25, okay. So this comes then back to me. So, and now I added 600. No, sorry, I didn't add 600. I added 598. Okay. So basically, everybody added his number, and the numbers that were shared are not revealing anything about the individual numbers. And now the last person can reveal. So if I subtract this from that, then we get what do we get? 169. That means this is the sum, and if we divide it by 6, then we get the average. What's the average? 3. 35 or so? I don't know. You all had mathematics. What is the average? Let me quickly compute it in my head. Okay. Good. So 28. So it is the average. So and the idea is that the numbers that have been passed on are not, they are not linked to the actual age or to the actual numbers. So if we want to compute as a group of at least 3 people, somebody starts with his own value plus a large random number, passes it on, so the own number is always added, and the last one is revealing the result minus the large number. And it uses some broadcast to share the results. It uses point-to-point communication for the direct interaction. And you need at least 3 parties, because otherwise, let's say you add 600 to 42 or 50, I don't know, and the next one adds 40. The result is revealed as being, so this is then cancelled out, 90. Obviously, if you know that there are only 2 parties, you can derive from that what the other person had. So you need at least 3 parties, but with 3 parties, you cannot simply recalculate what the other input was. It's a simple way to compute averages and sums, and also average and sum, let's say. There are various attack types. So if it's just semi-honest or passive, tries to gain information, then it's working. If it's malicious, aims to change the results. Obviously, if I add here as my age, I don't know, minus 60, then I change the result. But let's say the first step, that it is working against semi-honest computation parties, then it's valid. So, and this is the multi-party computation approach, where you basically trust that not every single one of the computing parties cheats. So if every single one of the computing parties reveal their numbers, I mean what R was, and then the next one can compute, basically they can compute step by step what the input was, then it's working. So it provides guaranteed output, correctness, and privacy, assuming that not all of them cheat. Independence of input, so you cannot base your input based on the input of others. So you cannot say my input should be the double of what the other provided. Computation with random aspect with secret shares that we will have a look at. And this has been also used in commercial environments. It's still used at the Boston University in combination with the city council, where they basically tried to identify the salary distribution of various companies in Boston. And one idea was there how to implement it is, so there has been some kind of, this is the actual data, so the yellow one, contributor A, contributor B, then there's a random mask. In this case, it's the big random number that is added to it. And then the mask data is added to the Boston University, which basically computes the values with the big random numbers in addition as well. In addition, what's happening is that the big random numbers are encrypted and passed on to some third party, where basically the third party is then computing the sum of all big numbers that everybody added, takes the sum of this mask aggregate data, which already contains the big is it even visible? So this red one, mask aggregate data, contains basically all salaries plus the big random number every time accumulated, and the blue is the big random number, which is then subtracted, and then you get the final output. And why is it privacy preserving? Because you don't know, is the data coming from contributor A or B, and if you have 1,000 contributors, then you just basically compute all the sums of all inputs. They all add this noise, and at the end you take this noise out, and you just learn the final result, but you don't learn what each individual data contributor provided. And the nice thing is, it scales to many data providers. So you don't have one key, one provider, and it's limited to one provider. It scales to thousands to millions of data providers. It's not limited. And these are simple computations, so there's no encryption involved. It's just addition of a big number. So easy to compute statistics. We will have a look at what happens if n gets large, n being the number of parties computing. Very simple operations only. So let's have an example how you could scale it also up to a large number of data providers. So what we want to have, again, think of this IoT scenario. You have many data providers, and you want to compute statistics on it. And we also learned if you have, okay, so let's see how we can organize it. Okay, yeah, let me just come back to this. Yeah, what was the trick here? So the trick was, yeah, this is the trick. So basically that you have a separation of one part of data, the red one, and the noise part of the data. So the red one contains the noise. So actual data, so basically what we have here is that the contributor A had the real data plus noise and a separate noise data. You could aggregate over this, then you get, I don't know, over many parties, the data and the noise, and you aggregate over all noises, and then you subtract it, and then you get basically the aggregate over the aggregate over all data. Yes, and this is the idea that you want to follow. So if we spread up our data, so if the data is here, we added noise and then we subtracted noise, but we could also think of such a case data. Let's make it different. So the main idea is to have random 1, random 2, and data minus random 1, random 2. You could, if you aggregate over the random value, aggregate over the random value 2, and aggregate over the random value and the data minus R2. Then if you sum it all together, you still get the data. And basically this idea that the noise has been introduced and then later filtered out, we want to introduce on a per data level. And this is the idea of privacy preserving computation on the multi-computational approach, and the multi-party approach. So the idea is, what you want to do, aim is to keep the input value secret, but to compute, let's say, the sum correctly. So what we do is we introduce a random value 1, random value 2, and this is the data minus random value 1 minus random value 2, so that if you sum them all up together, you get the correct result, in this case 10. So as you see, 80 plus minus 25 plus minus 45, this is equals 10. Yeah, this is our value. So we split it up and we store the data parts on 3 parties. This is for one user. Yeah, also here it is exactly. The next user does the same. The next user does the same. The next 1 million users do the same. What is now the trick? Now if we look at the sum, this is minus 89. Doesn't tell anything about the real values they had. The next party computes 100. The next party computes minus 21. So we have all these different sums that do not really correlate to what we have here. So each individual party did not learn anything special. But if we create with the age example what he had now, the sum over all of these 3 values, again, how was it done? So you take a very large number, minus 89. I don't know. Then you pass it on. Then this will be the large number, minus 89 plus 130. Then this is passed on large number, minus 89 plus 130 minus 21. And then you take the large number out here. Then you get the correct sum. And none of the parties learned what the input of the other parties was, because they had this large number to basically create the noise. They computed the sum correctly, and they computed the sum over the input values correctly. Although none of the 3 parties saw any kind of hint of real values from the data providing side. That's nice. So this is some kind of concept, at least for simple operations such as statistic calculation, that you can apply to support a large number of data providers, as long as, so when does the system break? The system breaks when party 1, party 2, and party 3 reveal their data at the same time to each other. So if only 2 parties reveal their data, they could still maybe learn what C1 was if some queries have been stated, if they learned some kind of results. But as long as none of, but still, they will not figure out what, let's say, the input of C was. I mean, only if each party in the computation agrees to cheat, then the system is broken. But otherwise not. So, what's the idea? The idea is to have this kind of, as long as there's a single honest participant, that's fine. The scales to potential millions, simple and fast, yeah. But only simple functions are supported. These shared secret approaches. Homomorphic encryption would be great. I mean, this is the big goal of secure computing. But it's either very limited or very slow. Garbled circuits even slower. I mean, it's very expensive to set up and to run, but can solve everything. Yeah. And encrypted databases, well, they have some kind of single user use case where you store your data somewhere else and you don't want to reveal what you store and you want still to do some computation on this. So this is some kind of contrast of use case. So these are, here you have n users, here you have one user. And homomorphic encryption and garbled circuits, especially this is powerful but slow. And this is limited but fast. Okay. Maybe to show you some lookout, why is this relevant? What is happening there? There's some kind of activity also ongoing. So Carbine Stack, for example, I will also talk about that. There's some kind of company consortium of various German and other companies who want to build some kind of reliable platform for secure computation, because this will become just an important element in the terms of EU regulations, how data can be treated, what you can do with it. There's some trend towards addressing the risk and containing the risk and telling, okay, this kind of computation happens all in secrecy and privacy, so we don't get access to it. Still the results are valuable, we can use it, but we don't learn, let's say, what individuals did, where they drove around, what kind of positions they had, what their individual data is, but we learn the results, and they can basically tell this kind of data is protected and we don't have access to it. So basically it's about, and this is the last slide on data and handling secure data and data computation. So there's always some kind of risk between data hoarding, then you have lots of value, but lots of risk of losing it. Or if you don't have data, don't have value, but also no risk of losing it. So it's really some issue how you can maximize the value while keeping the risk low. And all these multi-party computation approaches have the idea to get the results. If there are 1 million cars driving around and you would like to see what are the hotspots where the cars are driving, where should we put some ads or so, you want to just learn the results, but you don't want to learn where individual people drove around. So that might be some compromise. It works well for statistical analysis. Also heat maps, that's a 2D histogram. Or if the car manufacturers want to know what is the charging state of their car, so are they most charged, are they less charged, how much charging do they lose by driving a kilometer and so on, so to get real numbers. You want to learn the statistics, but not what individuals were having. Or privacy preserving anomaly detection, that's also happening. That's a common research field in network security as well, where basically you bring together the data of various intrusion detection systems of different companies, and you want to see what is common, what kind of anomalies do we see, what kind of common attacks do we face, without revealing what kind of individual local traffic you had. Some summary there, there's no solution to fit all scenarios, so you really have to see, do you have one single user scenario, then you have other kind of solutions that you can use. How essential is the functionality, so do you want to have Turing complete computations, such as with garbled circuits, then it's very slow, or is some kind of statistical analysis sufficient? And maybe to show you some short outlook at Carbine Stack, this is quite fresh and ongoing. They also want some kind of security award, I think in 22. There are some talk recordings available. What they do is especially building such a kind of environment where you can host your data computation platform, and as I've basically shown it, it's very similar to, you have 3 parties set up that are accepting queries and where you can upload data to in a split form, and then the queries are processed. So it's a little bit, there's a community ongoing. This is what I want to say, who's in the ecosystem maybe. Bosch, SAP, University of Sydney, Honda, And there's some other companies maybe also involved where the focus is on providing data, privacy preserving computation. So this is some ongoing topic. Okay, so far on this topic. I see we have some minutes left. I don't want to go too much into detail. I just want to sketch out what we will be talking about in the next week. We will talk about secure software development. I think this is also it's not really 100% related to network security, but if it's about building secure software, then I want to introduce you in the concepts of what to look for, and also, of course, network systems, what you should look for, how to build them, and what approaches are there. So especially, we will talk a little bit about threat modeling, how you build distributed systems. I mean, there's a saying that if you want to build a system, a distributed system, and they all have, every component has some kind of attack surface, some risk, what can happen. The errors you identify during the design phase are much easier to solve than if you try to correct your issues and open risks and open vulnerabilities during the implementation phase. I mean, obviously, you should, in the design phase, invest in threat modeling and identifying potential issues. And later on, we will look at how distributed systems as well can be systematically tested. And fuzz testing is the most prominent example there, finding the most bugs. So I want to introduce you into that domain. Okay. Obviously there are many other topics. Have you interacted with secure software development before? Any kind of pre-knowledge you have? Okay. That's good. So basically, to talk about this security development lifecycle that's for Microsoft. So, I mean, they are different. It's just a model that's just describing what kind of challenges they are and what steps in software development there is. So it basically tells, okay, people should be trained. Then, okay, let's build a system. Then we first collect the requirements. What should we? What do we plan to achieve? Sometimes I was talking about security requirements, quality gates, and so on. But let's say we talk just about what requirements you want to have. Let's say we want to build a website that receives IoT sensor data and visualizes the results. So somehow the sensor data should be stored somehow in a database. The database should be accessible by the web server, and it should be visualized. So we are now at the design. What components do we have? Which web server do we use? Then we should have a look at, is there some knowledge already existing, that's threat modeling, to basically visualize how our system should be sketched, that we have a web server, we have a database, we have an IoT device, we have maybe a user accessing the web server, maybe we have some, I don't know. And then which kind of communication channels do we have from IoT device to the web server, from the IoT device to the database, from the database to the web server. And then, do we have knowledge about database, I don't know, MySQL version 5.7? Are there some issues that we should look for? That's threat modeling. Then then we start implementing it. Maybe we need to write some code. How can we support our code writing process? Typically, there you have static analyzers. These are tools that highlight, as in Word, that you made a mistake, that you should not use this or that function, that you should take care that this method is, I don't know, private. So it's like a error correction for coders. And then we are at the verification phase. It's basically the software has been built, our system is set up, it can now be used. Dynamic analysis means, okay, let's test it for a while. We have pre-written tests where we want to analyze what's happening during that time. And fuzz testing is automatizing. It's basically generating millions of new inputs. So let's say we have this input from the IoT device to the database that should be then later visualized. what happens if we have malformed IoT device updates? So if the sensor data is malformed, and then it basically evolutionarily creates new input and tries to find something that causes a crash. And because you can, here you have probably, I don't know, hundreds of self-written tests. Here you have millions of tests. It's just, and if it finds some issue, then it also delivers you, this is the input that caused the issue. Yes, and then basically release plan, and this is more organizationally based, and also this organizationally, what happens if there's some issue. But in these two topics, because this is very crucial at the beginning, the more you find there as issues, the less you have later struggles. And fast testing, if everything is finished, that's the best way to find bugs, basically, that we will look into in the next lecture. So thanks for being here. See you then next week. Have a nice week until then, and yeah, have a nice time.